In this video, we will discuss character encoding. In a previous video where we discussed special sets, we introduced the set capital Blackboard A, which consists of the dash and all of the lowercase letters of the alphabet in traditional alphabetical order. Recall that the dash is used to indicate the character space and is not used as the dash in a traditional sense. In this video, we will discuss the topic of converting characters from the set Blackboard A into a series of numbers. To do this, we need to define a code. A code is a system of rules used to convert information from one form to another. The process of converting information into a new form is called encoding, while the process of converting information back to its original form is called decoding. To convert characters into numbers, we will use the encoding function C, which is a function from the set Blackboard A to the set zmod27. And to convert these numbers back into their original characters, we will use the decoding function C inverse, which is a function from zmod27 to the set capital Blackboard A. To encode characters into numbers, we use the function C, which takes elements in the set Blackboard A and sends them to corresponding numbers in zmod27. To do this, we send the character space to the number 0, and then send each letter to its corresponding numeric value in the alphabet. So, A is sent to the number 1, B is sent to the number 2, C is sent to the number 3, and so on, with Z being sent to the number 26. To decode the numbers back into characters, we use the function C inverse, which takes elements in zmod27 and sends them back to elements in the set Blackboard A. To do this, we send each number to its corresponding letter of the alphabet. So, 26 is sent to the letter Z, 25 is sent to the letter Y, 24 is sent to the letter X, and so on, with 1 being sent to the letter A. Finally, we send 0 to the character space. When performing your first few examples with this encoding and decoding function pair, it may be helpful to list the elements in each set and draw arrows between them to avoid errors in computation. Let's do an example to illustrate how this encoding and decoding process works. Let's use the function C to encode the phrase North Carolina into numbers, and then use the function C inverse to decode these numbers back into their original characters. If this is done correctly, we should recover the original phrase after decoding. Remember that the input into the encoding function C is a single element, not an entire phrase. So we will have to encode each character in the phrase North Carolina separately. Since N is the 14th letter of the alphabet, the image of N under the encoding function C is 14. The image of O under C is 15. The image of R under C is 18. And we can continue this process with T and H until we come to the character space, whose image under C is 0. Finishing the encoding with the remaining characters, we have the following sequence of numbers, which indicate the entire encoded phrase, North Carolina. Now, to decode these series of numbers back into the original phrase, we plug each of these numbers individually into the C inverse function and compute their images. The image of 14 under C inverse is N, the image of 15 under C inverse is O, the image of 18 under C inverse is R, and so on. Computing the images for the rest of the numbers, we see that the original phrase, North Carolina, is recovered, so our encoding and decoding was successful. Here are some examples for you to try on your own. Use the encoding and decoding functions provided to compute the following examples. Here are the solutions for each of these encoding and decoding problems.